Have you ever followed a recipe where you had to measure each ingredient exactly, like 2 cups of flour and 1 cup of sugar? Well, chemical reactions are just like recipes, but instead of ingredients, we balance atoms. Hello everyone. In today's session, we are talking about a fundamental concept in chemistry, balancing of chemical equations. Now, why do we even need to balance equations? That's because of a universal law, the law of conservation of mass, which tells us that mass is neither created nor destroyed in a chemical reaction. So, when writing chemical equations, we must ensure that the number of atoms of each element on the left-hand side equals the number on the right-hand side. Let me give you an example. Potassium dichromate plus hydrochloric acid gives potassium chloride, chromium trichloride, water, and chlorine gas. Clearly, this reaction is not balanced yet, the atoms don't match on both sides. And just like a recipe won't work if you add too much salt or too little sugar, a chemical reaction won't make sense unless all atoms are accounted for. To balance chemical reactions, one common approach is the hit and trial method. Let's see how it works. In this method, we adjust the coefficients, that is, the numbers placed in front of each compound, so the number of atoms of each element becomes equal on both sides. Let's return to our earlier reaction. K2Cr2O7 plus HCl gives KCl plus CrCl3 plus H2O plus Cl2. Step 1. Start by balancing the metal atoms. On the left, we have 2 potassium atoms and 2 chromium atoms in a potassium dichromate. So on the right, we place a coefficient of 2 in front of KCl and CrCl3. Next, balance the oxygen atoms. There are 7 oxygen atoms in potassium dichromate, so we place a coefficient of 7 in front of H2O on the right. Now, balance hydrogen atoms. 7H2O means we have 14 hydrogen atoms on the right. To match this, we place a 14 in front of HCl on the left. Lastly, balance chlorine atoms. 14 HCl contains 14 chlorine atoms. On the product side, we already have 2 from KCl, 6 from 2 CrCl3, and the rest 6 from 3 Cl2 molecules. That's a total of 14. So, the balanced equation is. Let's break this balancing process down step by step. Step 1. Potassium and chromium atoms. We have 2 potassium atoms and 2 chromium atoms on the left in K2Cr2O7. So we place a 2 in front of KCl and 2 in front of CrCl3 on the right. Step 2. Oxygen atoms. There are 7 oxygen atoms in K2Cr2O7, so we need 7 H2O molecules on the right to balance them. Step 3. Hydrogen atoms. 7 H2O contains 14 hydrogen atoms. That means we must have 14 HCl molecules on the left to supply the hydrogen. Step 4. Chlorine atoms. 14 HCl gives 14 chlorine atoms. On the right, 2 from KCl, 6 from 2 CrCl3 and 6 from 3 Cl2. That's a total of 14. Balanced. Final balanced equation. K2Cr2O7 plus 14 HCl gives to KCl plus 2 CrCl3 plus 7 H2O plus 3 Cl2. This type of reaction is often used in lab titrations and redox chemistry studies. Sometimes, especially in redox reactions, the hit and trial method becomes too complex. That's when we use the partial equation method. Here's the idea. You break the overall reaction into smaller, logical steps, each one easier to balance. Then, you cancel out any species that appear on both sides, like nascent oxygen, and combine the steps to form the final balanced equation. Let's look at an example when potassium iodide reacts with hydrogen peroxide. Instead of balancing it all at once, we write Step 1. Decomposition of hydrogen peroxide H₂O₂ gives H₂O plus O, where O is nascent oxygen. Step 2. Reaction of nascent oxygen with potassium iodide 2K plus O gives to KOH plus I2. Now we add both steps, cancel the oxygen, and we are left with 2K plus H₂O₂ gives to KOH plus I2. This method is logical and systematic, especially helpful when oxidation states are involved. Let's explore that potassium iodide and hydrogen peroxide example in more detail. Step A. Hydrogen peroxide decomposes H₂O₂ gives H₂O plus nascent oxygen, represented as capital O. Step B. Potassium iodide is oxidized by nascent oxygen to Ki plus O gives to KOH plus I2. Now we combine both steps to Ki plus H₂O₂ gives to KOH plus I2. We cancel out the oxygen since it appears on both sides, and the final balanced equation is complete. This reaction is important in iodometric titrations where iodine is liberated, and that iodine can then be measured to determine unknown concentrations. Now let's try something more advanced, the oxidation of hydrogen sulfide by potassium permanganate in acidic medium. Step 1. Acidified potassium permanganate releases nascent oxygen to KMnO₄ plus 3 H₂SO4 gives K2SO4 plus 2 MnSO4 plus 3 H₂O plus 5 nascent O. Step 2. Hydrogen sulfide reacts with nascent oxygen 5 H₂S plus 5 O gives 5 H₂O plus 5S. Now we combine both steps and cancel the oxygen. Final balanced equation to KMnO₄ plus 3 H₂SO4 plus 5 H₂S gives K2SO4 plus 2 MnSO4 plus 8 H₂O plus 5S. This type of reaction is used in qualitative inorganic analysis, especially to detect sulfide ions, which form yellow sulfur deposits. So let's wrap it all up. We started by understanding the law of conservation of mass and how balancing equations ensures that the number of atoms is the same on both sides. We explored the hit and trial method, where we adjusted coefficients to balance metal atoms first, then nonmetals, then hydrogen and oxygen. Then we moved on to the partial equation method, useful for redox reactions, breaking down the overall reaction into smaller steps, using nascent species like oxygen and cancelling intermediates. Let's recall the final balanced reactions we covered. K2Cr2O7 plus 14 HCl gives to KCl plus 2 CrCl3 plus 7 H2O plus 3 Cl2. To Ki plus H₂O₂ gives to KOH plus I2. To KMnO₄ plus 3 H₂SO4 plus 5 H₂S gives K2SO4 plus 2 MnSO4 plus 8 H₂O plus 5S. Each equation we balance tells a story of atoms combining, rearranging, and transforming into something new. So keep practicing and remember, a balanced equation is a heartbeat of every chemical reaction. I hope now you see that chemistry isn't just about memorizing formulas, it's about understanding how nature balances itself at the atomic level.